In my last video, I built a physics engine by looking into the future and making corrections in the present to improve that outcome. It worked pretty well, and it got me thinking, maybe I could use this same technique to control a physical creature, because we can look as far into the future as we want just by running the simulation ahead. So I could choose some random movements for this fish, but then only actually use the ones which get the fish closer to its goal. So the fish are made of these polygons, and I had to calculate whether or not the mouse was inside the polygon. And there's a pretty interesting method to do this. Imagine this laser beam fires off to the right, and we count the number of intersections with those line segments. If there's an odd number, then the mouse must be inside. So that's all the code that you need. Then I give the polygons a mass, which is the same as their area, and I can throw them around. To join the bodies together, I built these physics engine joints, and they work on the same principle as before. Look one frame into the future, and apply impulses in the present to keep the joints joined together. And they also have this angle limit mechanism, and that just prevents the fish from bending in impossible ways. So right now the fish is floating in space, but that's not what I want. I want it floating in water. So I had to calculate how these bodies interact with the water when they're moving. And originally I was coming up with pages of differential maths trying to solve this, but it was too complicated. So let's say this physical body is moving along the x-axis with a velocity of 1, and there's a plate attached to it which can interact with the water. So the water is moving against the plate in the opposite direction, and that gives the plate a force which is perpendicular. This gives the body a resultant force and a resultant anti-clockwise torque because the plate has an offset. So that gives me three numbers which create a row, and I can create another row for when the y velocity is 1, and another row for when the rotation is 1. And these three rows stick together to create a matrix. And all I have to do is multiply the current velocity by that matrix, and it gives me the resultant drag force. There was just one problem though. Let's say this plate is going through the middle of the body like this, and intuitively we know that that makes it hard to turn in the water because it's like a paddle. So why is the angular part 0? Well, the problem is we're only considering forces from the center of the plate. So the solution to this is to split the plate up into mini sections and calculate them all individually, which is actually doing the same thing as that differential maths I was trying to write earlier. So I put these plates all over the outside of the fish where the water's going to touch it, and the effect certainly looks very convincing, which is all we need. Now we need to motorize these joints in some way, and it can't just be random noise, it has to be more like a waveform. And I was wondering, how could I generate these waveforms? But then I realized I could just sample an audio track directly because there's all sorts of interesting shapes in there. So I downloaded some Mozart, and obviously we've all wondered what the music of Mozart looks like when it's played through a fish. This sampler has a dial for each motor, which just selects the position that it's playing from in the track, and then the motor just goes through it like a record needle. Obviously it's much slower because it's only doing 60 samples per second, whereas audio is usually played at about 44,000 samples a second. When I click the automatic button, what's going to happen is it's going to try some random values on those dials, simulate 1 second into the future, and if the fish gets closer to the goal, then it's actually going to use those values. So when we see the dials change, that's when it found better values. The thing is, we all know how a fish swims. It moves in a sine wave. So this one is more like a synthesizer, and it has one oscillator with a dial to control the frequency, and each motor gets its own phase offset and amplitude. And there's one more dial which controls which way the head is looking. The process here seems to be choose a frequency and base everything around that. So sometimes it chooses one that looks a bit silly. So I plotted a histogram of all the frequencies it chooses, and it seems to do its best work at slightly above and slightly below 2 Hz. And I was wondering, maybe this is similar to real fish. So this one is quite a big fish. It's 1.6 meters long, so it's more like a shark. But I found this paper here talking about tail beat frequency. And looking at this graph, if we look at the values for that length of fish, it matches up exactly. So maybe this simulation is actually quite accurate. I wanted to simulate multiple fish together, so I programmed some basic collisions between the physical bodies in this simulation. And so when it's looking into the future, it will actually see those collisions. And the cool thing is that I didn't have to write any new code or sensors into the fish to make it avoid other fish. The solution just appears naturally by itself. So I get to the end of this project, I'm editing the final video, and all of a sudden I realize that I've programmed this so that it's trying to get its average body position closer to the target. Surely it should be the head. So I made that change, and those parallel parking turns that it's doing turned into these beautiful movements. I find that really satisfying. I really loved this project. I think the fish ended up looking quite realistic. I have some more ideas for how to improve this. Maybe some different control schemes, maybe 3D. GPU accelerate the physics engine so I could simulate more fish and make them smarter. But for now I will leave you with the best part, which is these tiny fish. They're a lot of fun. So I hope you enjoyed watching.